Hey there, ladies and gentlemen, boys and girls. Today, we're going to use this video to kind of go over some of the basics about waves, talking about some of the basic stuff that we need to be able to understand about parts of a wave, their purpose, and some of the relationships between that determines the shape of the different types of waves out there. So let's get right into it. Nice thing about videos is that if I'm going to go over some of the vocabulary, which you should have done already, but if there's something I say that you need to supplement your notes or you forgot to add, pause the video. So I recommend having out your handy dandy notebooks out there and ready to go, and add anything that you feel is valuable. I'm going to try and hit some things, but part of this is going to be on you to kind of figure out what do you think is valuable and is important going forward. Or you can always just come back to this video later if you need to. So let's start talking about different parts of a wave. So let's start with the very basics first of all. So what I have here is kind of almost a little slinky style setup here, where there's no energy being used through it. The whole purpose of a wave is to transport energy from point A to point B. All right. So in this case here, if I wanted to transport energy, say from this hand all the way to the other side here. If I want to transport energy from one place to another, I'm going to use a wave to do that. That's how it always is. It's not just with slinkies and simulations. Literally, the sound waves are reaching you. The sound energy is leaving my mouth, using sound waves, turning into electrical energy in the microphone, well, actually mechanical energy into electrical energy, which is all mechanical waves, into electrical waves, so on and so forth. It's always some sort of wave that is transported. It's like the Uber car of energy, transports energy from A to B. So right now we are at what we call equilibrium. We're at rest. All right. And we can always tell because, there's this, no energy, there's no wave, there's no motion of anything like that. There's no energy being through it. All right. But if I were to put that wave into motion, this is a wave that we're all very familiar with. I'm transporting the energy. In this case, make sure I'm doing it this way. I'm transporting in one direction, but notice that the actual motion of the hand is going up and down. All right. Since the energy is moving one way and the hand motion is moving the other way, this is what we call a transverse wave, where the wave particle motion and the wave energy are perpendicular or right angles to each other. Doesn't matter which way you go, but they're always at right angles. All right. So in this case here, one of the first things you need to understand is some of the basic vocabulary parts of these waves. So for, this was part of your guys' assignment. Let's just talk about a couple of them real quickly. So the highest point of a wave is what we call the crest. All right. This is our highest point. It's the furthest point away from the equilibrium. And kind of as in the mirror image of it, all right, the crest is the farthest point from the equilibrium. We also have the furthest point in I guess you would say, in the negative direction. This is what we call the trough. Now, if you turned your camera upside down, or I turn this upside down, the crest would become the trough and the trough become the crest. They're just descriptors. All right. Either way, they are the furthest points away from the equilibrium. All right. And we can actually measure how far that is with something called the amplitude. The amplitude is either how far away the crest is, or how far away the trough is from that equilibrium. So how tall a wave is, basically, is what we're measuring there. All right. And then we have something called wavelength. So wavelength is exactly what it sounds like. It is the length of a single wave. And there's a couple ways to measure it. When you have a transverse wave like this, it is literally the measurement of the full wave. So all the way up, all the way down to the crest, and then back where it started, and then it would just repeat again. That length right there is called the wavelength. Right? It's how long each individual wave is, and it just keeps repeating. So I have a couple about 2.5 waves here shown on the screen. Now, there's an easier way to measure it. Some people, and including myself, like to measure it actually measuring, because it's the same thing, from crest to crest, or you can measure it from trough to trough. But either way, this is wavelength, which we represent with the Greek letter lambda, which should look familiar because it's actually the same letter that we use to measure half-life. It is what we call wavelength. It is the length of one wave, and there's a couple ways to measure it. All right. Now, that wavelength was one of the variables you were measuring in your guys' most recent lab about a wave. The other one was frequency. I'm going to need to start fresh here for frequency. All right, so frequency is a little bit trickier. Frequency is the number of waves per second. So you have two variables there to talk about frequency. It's not only the number of waves, but how long it takes to do that. All right, so the number of waves every second. The easiest way to do this is just to find a part of a wave. I like to do just the crest. So if I was going to measure, see, if I run the simulation again, how many waves are going to pass that star? And so I'm going to count the number of crests that are going to pass that star. I can count how many waves. It'd be 1, 2, 3, 4, 5, 6, 7, 8. All right, so I had 8 waves, right? Because I know how I set up this one. I had, in this case here, 8 waves. Oops. Oh no. Let's try that again. I pushed it with my hand. All right. So in this case here, I had 8 waves. We're letting this load back up. All right, sorry about that. All right, so in this case here, we had 8 waves. In this case here, it was actually 8 seconds. 8 waves in 8 seconds. What that gives me is a frequency of 1 hertz. Hertz are the units we use to measure frequency. Hertz is a shorthand of waves per second. So in this case, we had 8 waves in 8 seconds, or 8 waves per second. So in the most recent lab, what you guys had to do is you had to find the relationship between, what is the relationship between the wavelength and how many waves per second there were. It's past a certain point. All right. So let's try, let's reset this here. And I'm not going to actually do any calculations here, but we can start to see some of the basic stuff. Oops. So let's just, for the sake of doing this, let's make a little bit smaller amplitude, just to kind of show that example there, what it looks like to have a smaller amplitude wave. And also, I am not recording. Oh, am I? Yes, I am. Yes, I am. Okay. That would have been bad. Okay. I have a smaller amplitude wave here, and let's start it with the very low. If I have a very low frequency, in this case, I have a low frequency. Notice when I have a very low frequency, look at my wave. Look how long each one of these waves are. All right, that's a long distance between those waves there. All right, so a low frequency means a long wavelength. All right, with that said, if I were to have a higher frequency, notice how much closer together the waves are. All right, we have a much lower wavelength. So we're going to talk about sound waves. We're going to talk about light waves and different kinds. Mostly we're starting off probably talking about sound waves. All different sound waves are determined based on the this relationship between frequency and wavelength. The reason why I have a different sounding voice than somebody else is based on these frequency and wavelength of the sound coming out of my mouth. All right, those sound waves. And so we'll talk about that in the next video. But this is just some of the basic stuff so far, and we're gonna finish it up there for today. All right, if you need to go back and look at the notes some more, don't hesitate to do that. Make sure you've kind of got the big picture about the different parts and that relation to between frequency and wavelength. Otherwise, thank you, and I'll see you guys later. Good luck, and may the science be with you.